Okay guys, let's take a look at today's lesson. This is our fourth day in Taylor series. Fourth day. And what we're going to be referring to is something that we started talking about yesterday, and that is when it says find the sum of. In this case, we're actually going to find the sum, but we started talking yesterday if you've got that Maclaurin series for e to the x memorized, right, or probably close by now, and you have a bunch of terms. When it wants the sum of this series that you created is e to the x, and that is a concept that we have to have down before today. We were having some major issues with it this morning, so you've got to get that down. The sum of the series is the function that created the series. That is the sum. Now, if what I'm saying is making no sense, which perhaps it is not, you need to write that down. That's like a concept that you have to know. The sum of the series of this series is the function that created it. Now, sometimes we know the function that created it, and sometimes we don't. So, when you have a problem that says find the sum of, and it gives you a series, what it's asking you to do in a strange code, like math code, it's asking you to tell one of two things. Either you will be able to recognize the function that created this series, or it's geometric and we can use the formula for the sum of a geometric series. Those are really your only two options right now. So when that says find the sum of, and it's not talking about approximate sum or anything like that, it says find the sum of, it's going to be one of two things. It's either going to be the function that created it, that's considered the sum of the series, or it's going to be geometric. So with that said, let's take a look at these three examples that are asking us to find the sum of. There are another couple of ways that they might write this question. They may say find the value of, find the value of, and that's what they mean, find the sum of. They may say evaluate. So I'm just showing you a couple of different ways that this exact same question could be asked, and what they mean is what's the function that created it, or use the formula for sum for geometric. So let's take a look at our first example. One hint is to pay attention to the denominator. That usually will help you figure out which one it is. Either it's one that you've memorized, one of those three that you've memorized, so think back to the ones that you've memorized. If you haven't memorized them yet, just look back in your notes at those three and see if any of them look similar to that. Have a 1 factorial, a 2 factorial, a 3 factorial, an n factorial, e to the x. Now, to do these types of problems, you really don't have to show a lot of work. Sometimes really virtually no work. But I'm going to show you, since I'm real visual, I'm going to write down that e to the x equals just on this first one. So if you have your notes, it should be exactly what we have. It's e to the x equals 1 plus x over 1 factorial plus x squared over 2 factorial, and so forth, and then x to the n over n factorial. Alright, so we take a look, we're comparing this series to this series, and typically what will happen is they will, to change the way it looks, they'll substitute a number into the series that you've memorized. That's normally what happens. So if you look at the series that you have in memory, compare it to the one that they're giving us, what have they done? They've substituted a 3 in for x, haven't they? If you'll compare each of these terms, you'll see that they substituted a 3 in for x. So that's what we do when we say what the sum is. What's the sum of this series, the one we memorized? E to the x. So what is the sum of this series? E cubed, or e to the third. And you would just say sum equals e cubed. I mean, that's all you need to show. You don't need to show work for these problems typically. Okay, so now let's look at the second one. Look, again, focus on the denominators. That usually helps give you a clue on what's going on. Does that look similar to anything? Sine x. If you look back at your series for sine x, compare it to what you see here. What have they done to the series for sine x? They substituted a 2. That's exactly what they did. They substituted a 2 in that series for sine x. So with knowing that, the sum of the series that we are comparing to is sine x. So the sum of this series is sine 2. So the sum equals sine 2. Okay? Last one. This one isn't triggering or ringing any bells for me with the 3, the 9, the 27. But if you look at the general term, what can we tell from the general term? It's geometric. So this one we can find the sum by using that formula for the sum for geometric. So to use that, let's do that. Remember, the sum equals a over 1 minus r. In this case, a is 1. So a is 1 and r is negative 2/3. So our sum is 1 over 1 minus a minus, which is 1 over what, 5/3 or 3/5. So in this case, we actually have to do some calculations to find this sum because it's the second type that I was talking to you about. Okay? Okay? All right, let's take a look at this theorem. This theorem is an extension of the things that we've been working with. So let's take a look at it. So provided that we have a function that's written as a series, this should look familiar to you. That would be like a Taylor series centered at C. Provided that we have a function that's written as a series and has a particular radius of convergence that's larger than 0, then what they're telling us is we can take the derivative of this series or the integral of the series. And we practiced a little bit of that several days ago, taking the derivatives of series. We're going to do some more of that today. What this theorem tells us is that if we do that, if we take a series that we already know about or are given, and we take the derivative or the integral of it, that the radius of convergence is going to be the same. Okay, the radius of convergence is going to be the same as the original series that we were given. The interval of convergence, though, may be different. So the interval may be different, which means, endpoints, checking endpoints. There may or may not be an equal sign added to it or not. So basically, this theorem tells us that we can use the same radius of convergence to the original series, so we don't have to do that again, find the interval of convergence. It's just we have to check endpoints. That's what this theorem tells us. Okay? All right, let's take a look at the next page. All right, the first one. We have a function. It's defined by f of x equals 1 over 1 minus x. Okay, so when we develop a series for this is considered the sum of the series. Okay, I'm going to probably say that 20 times because that really is not sinking in to some of us. This is the sum of the series that I'm going to create. Okay? All right, so we want to write a Maclaurin series for that function and give the first 4 non-zero terms in the general terms and then find the convergence. So we could do derivatives and find the series the traditional way, but we learned a technique yesterday that might be helpful. Probably save us a little time. Right, we can write it like a geometric. We can use that geometric technique that we learned yesterday, where, remember, we compared it to the sum a over 1 minus r. I'm comparing a sum to a sum. You with me? This is the sum of the series. I'm comparing it to the sum of a geometric series. So a is going to be 1 and r is going to be x. So let's generate the series. We could say f of x equals, and let's do that because we're going to be doing some crazy stuff as we go on. So just say f of x, this is the original. So we start with 1 and then we multiply by x each time. So 1 plus x squared plus x cubed plus dot dot dot, and then x to the n is the general term that I'll use. Okay, so we have the answer to the first question. To find out if it converges, what do we do? Remember, that's right, we use the exact same stuff we worked with yesterday. We use the technique from geometric series and we set the absolute value of r less than 1. Now, for this type of series that we used the geometric series to create, do we need to check the endpoints? No, this is really the only time we don't have to check the endpoints. So we know that that is the interval of convergence. So it converges at -1 to 1. Okay, great. Now, we want to use the answer, so use the series that we got for f prime of x. We want to take the derivative of that series. Okay, so the most straightforward thing to do would be to take the derivative of each of the terms. So let's do that. So f prime of x would be, the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x, the derivative of x cubed is 3x squared, and I only have 3 terms, I need one more, so we'll just, that would have been x the fourth, so 4x cubed plus dot 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 plus. Now, the general term, I'm going to write it by really using the power rule, just like I did. So I brought the n down, x to the n minus 1. That's what we did to generate that. Now, my radius of convergence is going to be the same. I don't have to do a test or anything. It's going to be negative, well, the radius of convergence is 1. But I do have to check endpoints. All right. The nice little thing that we had going on with endpoints only applies to the very original one that you create. It does not apply to derivatives or integrals of that. So we're going to have to check endpoints. So let's do that. So when x equals 1, we would have okay, does this one alternate? No. So we can't use that test. What about nth term test? Can we use that one? Goes to infinity, so we can use the nth term test. So since this goes to infinity, does it diverge or converge? It diverges. So this diverges by the nth term test because We can do one of two things. We can write the limit out and say what it is, or we can say because the limit is not 0, does not equal 0. There are several ways that you could indicate that. So diverges by nth term test because the limit does not equal 0. That's one way to write it. Okay, so now let's check negative 1. When x equals negative 1, what do we get? We get that. Is that one alternating? Yes. So let's go through the test. It's alternating, yes. Is it decreasing in magnitude, the terms? No. So that test fails. So we can use nth term test. Right, on the nth term test, it still is going to diverge. So this one diverges by the nth term test because the limit does not equal 0. Okay. Now, on part C, this code word, what this is saying, this should be a code word that triggers what we just talked about. What is the sum of an infinite series? It's either the function that created it, a version of the function that created it, or it's geometric. Those are our options. So let's look at this one. Compare it to the function we just created. Notice anything? Now, let me give you some hints here. Normally, notice there aren't any x's here, right? This has x's, so what would they have done? They would have put something in for x, and in this case, they put in 1/3. Okay, they put in 1/3 for x, and it generated this. Okay, so this is f prime of 1/3. That's what that series is, right? That series is f prime of 1/3. Well, what does that mean? How are we going to find the sum? Yeah, we find f prime of x, we sub in the 1/3. That's how we're going to find the sum. Because the sum is the function that created it. And we just agreed, or maybe you were just humoring me, maybe you're like, what is she talking about? But we just kind of agreed that this function, this series, is f prime of 1/3. So we're going to take f of x, we're going to take the derivative of it, and we're going to put a 1/3 in there. Now, one other question. Do you think I'm allowed to put any number in there that I want? Exactly. I am not allowed to put any number in there I want, and neither are they. It can only be in the interval of convergence. Only in the interval of convergence. Our interval of convergence here is -1 to 1, so 1/3 is okay. Think back to the ones on the other slide. When they put 2 in sine of x, was that okay? Is that in the interval of convergence for sine of x? Yeah, because sine of x's interval of convergence is -∞ to infinity, so that was okay. All right, so let's find f prime of x. First of all, I'm just going to rewrite f of x as 1 minus x to the -1, just so it's easier. Okay? So let's find f prime. So -1 minus x to the -2, and then I chain it. Alright, now finding f prime of 1/3, I would get so 9/4 is the sum of this series. Okay? Or it could have said evaluate or, one of those other terms that I told you. That is the sum of this series. Okay? All right. Now, I know this has been lots of fun. We're getting ready to have even more fun because they're going to ask us to integrate the series. Yay! Now we're going to integrate the one that we made at the beginning. Okay. So for those in the back, I'm going to actually erase so I can write up higher. Is there anybody that still needs this? Why is what? I chained it. I have to do the derivative of the inside is -1. Okay. So are we all okay? Everybody good? All right. I need to get some room so I can do this integral up higher up here. So let's get rid of all this. All right. Let's start again. So we're going to do this. Okay? We're going to find the integral from 0 to x of f of t. All right, so let's do that. Okay, that's what they're asking us to do. Okay, so we're going to integrate the series that we created. Now they want us to use t's instead of x's, and that's fine. We'll do that. And now we're going to do our integration, our reversal power rule, and integrate those guys. So let's do that. Okay. So we integrated. This is a really messy n plus 1. Okay. All right, now we do our f of b minus f of a. Luckily, a is 0, so that's not going to create any additional terms. So let's do our f of b minus f of a, and we get okay, and that is the first 4 non-zero terms in the general term. I changed up the general term just a little bit. That's an okay general term. It means the same thing as the one that we started with. What is the difference between those two? Yeah, where the n starts. And so I just changed it, whichever way you like. It's again, as we talked about, the author of this general term knows where the n started, and other people can usually figure that out. All right, so that's one answer. Now we're going to look at convergence. So it wants to know, for what values of x does the series converge? Well, we know the beginning of it, right? I mean, we know that. We don't even have to do the different tests. We did the ratio test to determine. We don't have to do that. We already know that. The only thing we are going to have to do is check endpoints. So let's check the endpoints. So when x equals 1, we have this series. So we substitute a 1 in for x, we get that series. What's that series? Is that one going to diverge or converge? Diverges. A couple of different ways you can say it. What's one way? It's a p-series with a p of 1. It's a divergent p-series. You can say that it's a harmonic series. They like that name, so I mean you can just, we know the harmonic series diverges. So either way, we can say it diverges because it's the harmonic series, or you can say it diverges because, you know, it's a p-series with a p of 1. All right, let's check negative 1. When x is negative 1. All right, so then we have this. Okay, what kind of series is that? It's alternating. So let's do the alternating series test. It's alternating. Are the terms decreasing in magnitude? Yes. Is the limit approaching 0? Yes. So therefore, what does this series do? This series converges. So this one converges by alternating series test because it's alternating, check. It decreases in magnitude, check, and the limit is 0, check. So that, what does that mean? That means that we add an equal sign up here. Yay! That's our convergence. Woohoo! All that for the equal sign. All right. Last question. Okay, look at the code words. Use your answer to D, the one that we just did, to find the sum of the infinite series. To find the sum means figure out which function created it. Okay, so look at the series that we have up there. Compare it to this picture of the series. Can you tell what this is? Yeah, it's the integral. It's this guy right here, isn't it? It's the integral taken, basically 1/3. 1/3 is put in the series, right? An x of 1/3. Is 1/3 in the interval? It's in the interval, right? It's right here. It's in the interval, so we're okay. So how in the world am I going to find the sum? Absolutely, I have to take the integral of f of x, because that's how this was created, right? It's the integral of f of x. So let's get the first part. So the integral of f of x, which is 1 over 1 minus x, and I'm going to take it from where to where? 0, because I'm matching this, to 1/3, because isn't that what x is? 1/3. So 0 to 1/3. And we get to remember our fun integration. What is the integral of that? Yep, negative ln 1 minus x, evaluated from 0 to 1/3. So we do that, and we get negative ln of 2/3 plus ln of 1. What's ln of 1? 0. Now, negative ln of 2/3 is the answer, but you know they're not going to write it like that. They would take this negative and pull it up into the argument. Yep, and they would make it ln of 3/2. That's what they would do. Now, I'm not going to count off if you give that to me as an answer. I'm just saying that's normally not how they would write it. They would write it like this. Whew. All right.